It was the Fortress, a four-engine Titan designed to blacken the skies over Germany. On paper, it was a masterpiece of aeronautical engineering, but on the factory floor, it was a failure. While generals demanded bombers, America's greatest industrial weapon was being crippled not by enemy fighters, but by a simple blueprint. The fate of the air war wouldn't be decided by an ace pilot or a grand strategist, but by a man with a rivet gun who dared to say the experts were wrong. In the dark, early months of 1942, the United States was a giant awakening to a world on fire. The shock of Pearl Harbor had given way to a grim reality. The nation was dangerously unprepared for a two-front war. In Europe, the situation was dire. The British were fighting for their lives, and the Soviet Union was reeling from the German onslaught. The Allies' grand strategy depended on a weapon that could strike directly at the heart of the Third Reich, a weapon that could cripple its industrial might from the sky. That weapon was the Boeing B-17 Flying Fortress. It was more than an aircraft. It was the physical embodiment of American air power doctrine. General Henry Hap Arnold, the commander of the Army Air Forces, had staked his career on the concept of high altitude, daylight precision bombing. He envisioned fleets of these heavily armed bombers, flying in tight formations, capable of defending themselves while systematically dismantling Germany's war machine. The B-17 was the key to this entire strategy, the long-range sword that could reach out and break the enemy's will to fight. There was just one catastrophic problem. America couldn't build them fast enough. From his office in Washington, General Arnold saw a terrifying gap between his strategy and his arsenal. He needed hundreds, then thousands of B-17s to fill the skies over Europe and the Pacific. But the production numbers coming out of Boeing's vast Plant 2 in Seattle were a trickle, not a flood. In January of 1942, a month after America entered the war, the factory was producing a mere fraction of the bombers the military desperately required. The plant itself was a marvel of the age, a cavernous space where the industrial might of a nation was being focused on a single purpose. Thousands of men and women filled with patriotic fervor worked around the clock under the slogan, "The more B-17s, the sooner victory." Yet for all their effort, a hidden anchor was dragging the entire enterprise to a near standstill. The problem was not a lack of parts, or a shortage of labor, or a flaw in the raw materials. The bottleneck, the single point of failure choking the life out of the production line, was the wing. The wing of a B-17 was an immense and complex structure, an engineering triumph over 100 feet in length. It was this wing that allowed the Fortress to cruise above the reach of enemy flak, to carry its bomb load for thousands of miles, and to absorb incredible punishment, and still bring its crew home. Its strength was paramount, and the engineers who designed it, guided by the advanced aerodynamic theories of men like Theodore von Karman, had left nothing to chance. They had devised a meticulous, sequential riveting pattern. Each rivet was a point of strength, and the pattern, a series of precise, parallel rows, was calculated to distribute stress across the aluminum skin with mathematical perfection. It was a design of theoretical elegance, born from slide rules and stress diagrams. But on the loud, chaotic, and greasy reality of the factory floor, this elegant theory was an operational disaster. The mandated pattern forced teams of riveters to work in a slow, frustrating sequence. One team had to complete an entire row before the next could even begin their work on an adjacent one. This created a constant logjam. Skilled workers would stand idle, waiting for a small section of the massive wing to be completed, unable to move to other areas. It was like trying to paint a giant mural with a dozen artists who were all forced to share a single brush. The result was a staggering 20 hours of labor for each wing. This single, agonizingly slow process was the sand in the gears of America's war machine. And with each passing day, the demand for bombers grew more desperate, and the crisis on the factory floor deepened. Amidst this grand failing orchestra of industry was a man named Frank Schimanski. He was not an engineer, not a manager, and certainly not a strategist. He was a riveter, a man whose world was measured in the precise bucking of a rivet gun and the smooth, flush finish of a perfectly set fastener. Every day he was a foot soldier in the war of production, his hands shaping the very machines that would carry the fight to the enemy. But unlike many, Schimanski possessed a trained eye for a different kind of combat, the war against inefficiency. He had come to Boeing from the crucible of American manufacturing, the high-speed, high-pressure, automotive assembly lines of Detroit. There, the gospel was motion. The line never stopped. Every action was choreographed. Every second was counted. And the idea of a skilled worker standing idle was industrial heresy. On the floor of Plant 2, Schimanski saw heresy everywhere. He watched the frustrating, inefficient ballet forced upon his fellow workers by the blueprint. He saw teams of men, their rivet guns silent, their hands in their pockets, waiting for another crew to painstakingly finish a long, straight line of fasteners. They were log jams of humanity, clustered around one small section of a wing that was over 100 feet long. To Schimanski's Detroit-trained mind, this was insanity. An automobile with its complex chassis, engine, and bodywork came together in a symphony of parallel activity. Different teams swarmed the vehicle from all sides, each performing their task simultaneously. Here, they were building a comparatively simple aluminum surface, yet they were forced to do it in a slow, single-file march. The engineers, he knew, had their reasons. Their pattern was a thing of theoretical beauty, designed for optimal load distribution and structural integrity in the violent skies over Europe. But they had designed a wing without considering the human beings who had to build it. They had created a perfect product that was impossible to produce efficiently. Day after day, the frustration gnawed at him. He saw the exasperation on the faces of his colleagues, felt the lost hours hanging heavy in the air. This wasn't just slow. It was a critical vulnerability. Every B-17 delayed on this factory floor was a victory for the Axis. One day, during a break, surrounded by the metallic skeleton of a future bomber, he could stand it no longer. He pulled out a stub of a pencil and a crumpled piece of paper. He wasn't thinking about aerodynamics or stress coefficients. He was thinking about access. He was thinking about flow. Instead of the rigid, parallel rows, he sketched a new pattern. It looked almost chaotic, like a spider's web or a constellation of stars. He divided the wing into sections, creating zones where different teams could work at the same time, moving from the inside out or from the center to the tips without ever getting in each other's way. His design was not based on the physics of flight, but on the physics of people. It was a pattern for workers, not for a wind tunnel. He looked at his rough sketch, a simple idea that seemed to cut through the knot of the entire production crisis. It was a radical departure from established aerospace doctrine. It was unauthorized. It was, by the book, wrong. And yet he knew with the certainty of a man who worked with his hands that it would work. He folded the paper, the blueprint for a manufacturing revolution, in his pocket, and went to find his supervisor, a man named Bill Hendricks. He was about to break the chain of command, armed with nothing more than a pencil sketch and an idea born from the factory floor. Presenting an unsanctioned, hand-drawn schematic to a supervisor in the rigid, hierarchical world of wartime production was a significant gamble. Frank Schimanski was not merely suggesting a minor tweak. He was challenging the very foundation of the engineering department's authority. He was an hourly worker telling the salaried, university-educated experts that their core design philosophy was flawed. Bill Hendricks, his supervisor, was a man caught in the middle. He was responsible for the daily, grinding reality of the production targets, and he felt the immense pressure from management as those targets were consistently missed. He listened to Schimanski, not with the immediate dismissal of a bureaucrat, but with the weary attention of a man desperate for any solution. As Schimanski unfolded his crumpled sketch and explained the logic, not of aerodynamics, but of human movement, Hendricks saw the sheer, practical genius of it. It was a worker's solution to a worker's problem. The idea was simple. Instead of a single, continuous path, Schimanski's pattern created multiple starting points, allowing crews to attack the wing from several directions at once. It was a frontal assault on the assembly process rather than a slow, sequential siege. Hendricks knew the risks. Approving this would mean defying a direct engineering mandate, a move that could cost both him and Schimanski their jobs. The engineers guarded their specifications with zealous authority. Their calculations were law. Yet the crisis on the floor was undeniable. The official method was failing, and the pressure from the top was becoming unbearable. The risk of inaction, of letting the bottleneck continue to strangle the war effort, seemed even greater than the risk of insubordination. Hendricks made a calculated decision. He took Schimanski and his sketch up the chain of command to a man named Donald Douglas, the assistant production manager. Douglas was a man living in the eye of the storm. He was the one who had to answer to Boeing's executives and, by extension, to General Arnold's office for the catastrophic production delays. He was less concerned with theoretical perfection and more with the cold, hard numbers on his daily reports. When Hendricks and Schimanski laid out the proposal, Douglas saw not a violation of protocol, but a potential lifeline. He recognized the elegant simplicity of the idea and, more importantly, the potential for a dramatic increase in speed. The official channels were too slow. Getting the engineering department to review, test, and approve a new pattern could take months. Months the Allies did not have. A bold and frankly dangerous decision began to form in Douglas's mind. He couldn't authorize an official test without alerting the very engineers whose design they were trying to circumvent. It had to be done in secret. Douglas looked at the two men before him, a floor supervisor and a riveter, and saw the kind of pragmatic ingenuity that the crisis demanded. He gave the order. They would conduct an unauthorized trial. They would use a wing that had already been rejected by quality control for minor defects, a piece of scrap destined for the junk heap. The test would take place during the graveyard shift in the dead of night when the cavernous plant was quiet and the prying eyes of the engineering staff were absent. It was a conspiracy born of desperation, a secret pact between three men at different levels of the factory hierarchy, united by the common goal of getting the bombers built. On the night of February 21st, 1942, as the rest of Seattle slept, Schimanski, Hendricks, and a hand-picked crew of trusted riveters gathered under the dim lights of Plant 2. Their work area was a clandestine laboratory, their test subject a piece of industrial scrap that held the potential to alter the course of the war. The air was thick with tension and the smell of machine oil. They were about to put a riveter's intuition up against the established science of aerospace engineering. The graveyard shift began. The sprawling factory, usually a cacophony of roaring machines and clattering tools, was an echoing cathedral of metal. Schimanski and his covert team approached the rejected wing. It lay in its jig, a colossal metal skeleton waiting to be given its skin. This piece of aluminum, deemed unworthy for flight, was about to become the most important B-17 wing in history. Schimanski, no longer just a riveter, but now the choreographer of this secret ballet, laid out his hand-drawn pattern. With chalk, he and Hendricks marked the new starting points, creating multiple independent work zones across the wing's vast surface. There were no complex instructions, no dense engineering manuals. The logic was visual, intuitive. Instead of lining up in a frustrating queue, the riveting teams spread out, each taking charge of a designated section. The signal was given, and the silence was shattered. A chorus of pneumatic rivet guns erupted, not in the slow, staggered rhythm of the day shift, but in a sustained, thunderous roar. It was the sound of unleashed productivity. For the first time, multiple crews worked on the same wing skin simultaneously, their movements independent yet coordinated. One team started near the root, another worked out towards the tip, a third tackled the trailing edge. There were no collisions, no waiting, no bottlenecks. The men moved with a speed and efficiency that felt liberating. Schimanski's theory, born on a scrap of paper, was coming to life in a symphony of synchronized labor. Donald Douglas watched from the shadows, a stopwatch in his hand, his expression a mixture of anxiety and hope. The minutes ticked by, turning into an hour, then 2. What he was witnessing was not just a faster process, it was a fundamental transformation of the workflow. The constant, frustrating stop and start that had plagued the assembly line was gone, replaced by a smooth, continuous application of force. The hours of idle time, where skilled men waited for others to clear a path, had evaporated. As the final rivet was driven home, a new silence fell over the workspace. The stopwatch was clicked. Douglas stared at the result, scarcely believing the numbers. The official process, the one mandated by the brightest minds in aeronautical engineering, took 20 agonizing hours. Schimanski's illicit method had taken just over 2. It was a staggering, near 10-fold reduction in assembly time. A revolution had just occurred in the dead of night, but speed was only half the battle. A wing built 10 times faster was useless if it couldn't withstand the stresses of combat. In fact, the engineers would argue that such a rapid, unorthodox assembly must have introduced hidden weaknesses into the structure. The next morning, the wing was quietly moved to the stress testing rig, a massive hydraulic machine designed to simulate the brutal forces of flight and combat maneuvers. This was the moment of truth. The official 20-hour wings often came to the rig with a significant number of defects, misaligned rivets, dimpled skins that had to be reworked. The inspectors began their examination of the test wing, expecting to find a disaster. Instead, they found the opposite. The defect rate was 90% lower than average. The smooth, uninterrupted workflow had resulted in higher quality, more consistent work. Then came the ultimate test. The rig began to apply pressure, bending the wing to its breaking point. The engineers who had designed the original pattern knew exactly how much force their wings could handle. As the hydraulic pressure mounted, far exceeding the design specifications, the test wing refused to fail. It groaned, it flexed, but it held together with astonishing resilience. When it finally did fracture, it had endured a load significantly greater than that of any wing built using the officially sanctioned method. The Riveter's pattern was not just faster, it was stronger. The results of the secret test landed on the desks of Boeing's management like a controlled detonation. The data was irrefutable. A 90% reduction in assembly time, a 90% reduction in defects, and a significant increase in structural strength. Donald Douglas, armed with this explosive proof, bypassed the entire engineering department. He went directly to James Murray, Boeing's formidable vice president of operations. Murray was a man who understood that the war would be won or lost on the factory floors of America. He was less interested in theoretical debates than in the stark reality of production quotas. When presented with the story of the graveyard shift test, he didn't see insubordination. He saw a miracle. He saw the key that could unlock the single greatest obstacle to Allied air supremacy. The reaction from the engineering department was exactly what Hendricks and Douglas had feared. It was a storm of professional outrage. They were apoplectic. To them, this was not an innovation. It was an act of industrial anarchy. A floor worker, a man with grease under his fingernails, had presumed to rewrite their carefully calibrated formulas. They protested that this new pattern, conceived without stress analysis or wind tunnel data, was a reckless gamble that could endanger the lives of air crews. They argued that the test on a single, rejected wing was an anomaly, not a scientifically valid proof. Their professional pride was wounded, and their authority had been openly challenged. They demanded a halt to this rogue procedure and a return to the approved, albeit disastrously slow, method. But James Murray was already looking past their objections. He was looking at the calendar. He was looking at the telexes from Washington, pleading for more bombers. He understood the engineers' perspective, their adherence to process and scientific rigor. But the stopwatch and the stress rig told a more compelling story. He made a decision that was as swift and decisive as the test itself. On February 25th, 1942, just 4 days after the clandestine experiment, Murray issued a plant-wide directive. Schimanski's pattern was to be implemented on the entire B-17 production line, immediately. There would be no further debate. The change was implemented with the force of a military command. Blueprints were redrawn overnight. Supervisors, including a vindicated Bill Hendricks, fanned out across the factory floor, teaching the new intuitive method to every riveting team. The effect was not gradual. It was instantaneous and transformative. The bottleneck that had choked Plant 2 for months simply vanished. The colossal B-17 wings, once a symbol of industrial frustration, began to flow off the assembly jigs with breathtaking speed. The change rippled outwards, accelerating every subsequent stage of production. Fuselage no longer sat idle, waiting for wings to be attached. Final assembly hangars, once sparsely populated, began to fill with gleaming new bombers. The numbers told the story. In March of 1942, the month after the new pattern was adopted, B-17 production jumped from 47 to over 70. By September, the plant was turning out an astonishing 362 flying fortresses a month. A factory that had been failing its nation was now a fountain of air power, producing bombers at a rate that had seemed impossible just weeks earlier. The sound of Frank Schimanski's revolution was the ever-growing roar of Wright Cyclone engines as squadron after squadron of new B-17s lifted off from Boeing Field, destined for the skies of Europe. The solution had been there all along, not in a laboratory or a research paper, but in the mind of a worker who understood the rhythm of the line. The exponential increase in B-17 production was not merely a triumph of manufacturing, it was a strategic weapon in its own right. Across the Atlantic, the 8th Air Force, America's primary strategic bombing arm in Europe, was desperately trying to build its strength. In the summer of 1942, it was a fledgling force, capable of only limited small-scale raids. General Arnold's vision of massive bomber formations overwhelming the Luftwaffe remained a distant dream, crippled by the simple lack of aircraft. The bombers trickling out of Seattle prior to Schimanski's innovation were not enough to replace combat losses, let alone build the overwhelming force needed to execute the Allied bombing strategy. But as the floodgates opened at Plant 2, the dynamic began to shift. Throughout the latter half of 1942 and into 1943, a steady stream of flying fortresses poured across the Atlantic. Air bases in England, once home to a handful of squadrons, swelled into bustling cities of aviation. The mighty 8th was finally being forged, not just in training, but with the sheer mass of steel and aluminum now arriving daily from the American mainland. This growing arsenal enabled the 8th Air Force to escalate its campaign, moving from tentative strikes on coastal targets to daring, deep penetration raids into the heart of Germany. The increased availability of aircraft meant that losses, though brutal, could be sustained. Damaged bombers could be replaced and new crews could be equipped. The air war became a brutal calculus of attrition, and thanks to the revolution on the factory floor, it was a calculation that was now tipping in the Allies' favor. The ultimate proof of this newfound power came in the summer of 1943. Allied strategists conceived one of the most audacious and dangerous air operations of the war, a simultaneous double-strike raid against critical German industrial targets. The mission called for a massive force of B-17s to attack the Messerschmitt fighter aircraft factories in Regensburg and the vital ball-bearing plants in Schweinfurt. These targets were essential to the German war machine, and they were defended by the deadliest concentrations of Flak and Luftwaffe fighters in Europe. To execute such a mission, to absorb the inevitable horrific losses and still inflict decisive damage, required a scale of force that would have been unimaginable just a year prior. On August 17, 1943, the Schweinfurt-Regensburg mission was launched. A staggering 376 B-17 flying fortresses thundered into the sky from the bases across England. It was a physical manifestation of America's industrial might, a sky-darkening armada made possible by a riveter's chalk marks on a factory floor. The raid was a brutal ordeal. 60 bombers and their crews, nearly 600 men, were lost in a single day of savage air combat. But the mission succeeded in its objective, inflicting crippling damage on German production. More importantly, it demonstrated that the 8th Air Force could now project its power anywhere over the Reich, absorb staggering losses, and return to fight another day. Every single one of those 376 bombers that flew that day was a direct descendant of the secret graveyard shift experiment. The courage of the air crews who flew through storms of flak and fighter attacks is legendary. But their bravery would have been strategically irrelevant without the sheer number of aircraft to fly. The path to the skies over Schweinfurt began in the quiet of a Seattle night, with a man who refused to accept that the right way was the only way. The roar of hundreds of engines over Germany was the echo of one man's revolutionary idea. The story of Frank Schimanski and the B-17 wing is more than just a dramatic wartime anecdote. It stands as a pivotal, real-world lesson in manufacturing philosophy. It became one of the foundational examples of a principle that would later be given a formal name: Design for Manufacturability, or DFM. In the decades before the war, the worlds of the engineer and the factory worker were sharply divided. The engineer was the thinker, the theorist, the one who created the perfect object on paper. The worker was the doer, the assembler, the one whose job it was to simply follow the blueprint, no matter how impractical or inefficient it might be. This created a fundamental disconnect, a wall between the clean room of design and the noisy floor of production. The original B-17 wing pattern was a classic product of this old philosophy. It was theoretically perfect in terms of its final performance, but practically disastrous in its execution. The engineers had solved the aerodynamic and structural problems with brilliance, but they had completely ignored the human problem of how to actually build the thing. They had designed a product, not a production process. Schimanski's innovation was not about redesigning the wing itself. He didn't change a single material or alter the final shape. Instead, he redesigned the process of its creation. He tore down the invisible wall between the blueprint and the builder. His solution instinctively understood a core tenet of modern DFM, that the ease, speed, and quality of assembly are as critical to a design as its theoretical performance. By considering the accessibility for workers and the flow of the assembly line, he created a product that was not only faster to build, but also demonstrably better and stronger. The secret test on that February night was a powerful, if unintentional, scientific experiment. It proved that involving the practical knowledge of the assembly line worker was not a concession, but a competitive advantage. It demonstrated that the person with the tool in their hand often possesses insights that are invisible to the person with the slide rule. The successful implementation of his pattern forced a seismic shift in thinking at Boeing and eventually across the entire aerospace industry. The company began to formalize this collaboration. Engineers were encouraged, and later required, to spend time on the factory floor, observing the assembly process and soliciting feedback from the workers. Production line veterans were brought into the design phase, their practical experience valued alongside the theoretical calculations of the engineers. This feedback loop, this direct line of communication between the designer and the builder, became a cornerstone of post-war American industrial excellence. It influenced the development of everything from the B-29 Superfortress to the jet airliners that would eventually shrink the globe. The legacy of that single, unauthorized act of ingenuity is still visible today. In modern aerospace, automotive, and electronics manufacturing, DFM is a fundamental discipline. Products are now designed concurrently by teams of engineers, manufacturing specialists, and even supply chain experts. The goal is to create a design that is not only brilliant in function, but also elegant in its simplicity to produce, test, and maintain. Every time a company simplifies a design to reduce the number of screws, or alters a component's shape to make it easier for a robot or a human to install, they are walking in the footsteps of Frank Schimanski. He didn't have a name for it, but on a cold night in 1942, he proved that the shortest path to building a better weapon was to listen to the builder. The scale of the Second World War was so immense, its battles so vast and its leaders so iconic, that it is easy to overlook the contributions of individuals far from the front lines. The narrative of the war is often told through the grand movements of armies and the solemn decisions of generals. Yet, victory was forged not only in the cockpit of a fighter or the turret of a tank, but also in the minds of those who solved the colossal logistical and industrial puzzles that powered the Allied war effort. Frank Schimanski was one such hidden architect of victory. He never flew a mission, never faced enemy fire, and his name is not etched onto the grand monuments of the war, yet his contribution was as tangible as any bombing raid. By seeing a flawed pattern and having the courage to challenge it, he directly enabled the production of thousands of additional B-17s. Each of those bombers represented 10 crewmen sent into combat, a 5,000-pound bomb load delivered to a target, and a vital component in the relentless air campaign that ultimately broke the back of the German war machine. His story serves as a powerful reminder that wars are not won by weapons alone, but by the systems that create them. The B-17 was a magnificent aircraft, but without an efficient means of mass production, it would have remained a boutique weapon, unable to generate the overwhelming numbers needed for strategic effect. The true secret weapon that emerged from Boeing's Plant 2 was not a new type of bomb or a more powerful engine. It was a new way of thinking. It was the understanding that the genius of the common worker, the practical wisdom of the person on the line, is a strategic resource of immeasurable value. The conflict was a war of systems, democratic versus totalitarian, industrial versus industrial. America's ultimate advantage lay in its ability to adapt, to innovate, and to harness the ingenuity of its entire population. The tale of the impossible pattern is a perfect microcosm of that advantage. It is a story of how a rigid, top-down, theoretical approach failed, and how a flexible, collaborative, and practical solution triumphed. It underscores that in any great endeavor, whether a global war or a complex engineering project, the view from the ground is just as important as the view from the top. The flying fortresses that darkened the skies over Europe were monuments of aluminum, but they were also monuments to an idea that the person who builds the thing might just know a better way to do it. It was an idea sketched on a scrap of paper, tested in secret and ultimately vindicated in the fires of the largest industrial conflict in human history.